Hello YouTube viewers, welcome to my show Computer Wednesday. In today's episode we're gonna take a look at submersion cooling because it's becoming the next big thing. So let's dive right into it. So why there is a need for submersion cooling? Well, first you have to understand every sort of compute device like your CPU, your GPU, these are compute cards. As you can see, they don't have display output. They're compute card. Basically, they do the computation. They're becoming very power hungry. Now, many of you might find that odd that every year you say this processor is more energy efficient, more energy. How the heck they end up consuming more power? It's simply because how computer chips are made, as many of you have seen, there is a sort of wafer, silicon wafer that they do that. Now, since we can make the transistor made out of those wafer very small, we tend to pack them very closely. So each generation, even though it's getting more energy efficient, we end up packing so much in one processor that it ends up consuming too much power. And consequence of that we are packing so much, it also becomes hot. Not because it's inherently hotter. The transistor in one versus transistor in another, they are same. Problem is they are so compactly tightly knit together that they need high level cooling. Otherwise, they will simply melt. They will literally melt themselves. So because of the this demand, the processors right now, like this AMD Threadripper processor can reach upwards of 300 to 500 watts of power consumption on one device. Many of the Intel server grade system can also reach 3 to 400 watt. Not for the server one, but for supercomputer ones, they can reach that high. So suffice to say, as power requirement of the computer era is going up, like really, and let's just not try to talk about these. Each of them can easily consume upwards of 1 kilowatt. So suffice to say, the processors, the actual compute units are becoming more power hungry, and we are also becoming more and more digitized, so we need more processing power. YouTube needs processing power, Facebook needs processing power, Google needs processing power. So there is a demand for more processing power. And then we come to the new kid in the town, which is artificial intelligence and big data. So for last 10 to 20 years we've been collecting data. Now this data requires very severe number crunching, and I'm talking billions of data point crunched in an hour. So suffice to say, because of big data, you need a big computer to handle that, and this creates a requirement for supercomputers. And artificial intelligence is a very new frontier, but it's going to need very high-end computers, simply because, as many of you have seen recently, Google AI can actually cross the Turing test and flat out talk to a human as a human. So how does this thing work? One thing you have to understand, we are still doing what's called air cooling. Only difference is we are cutting out the middleman. This is the crucial aspect. So earlier we used to have a server room, a refrigerator unit, and then exhaust is going out of wherever you could have cooling towers, you can have simple radiators, whatever you have. So we are still using that. Only thing we are changing is that from the evaporator side, which basically becomes the cold end of the system, we are directly trying to link that cold end of the system to the hot end of the computer unit. Basically we are trying to connect them, and generally this connection happens through air. Now we are like, okay, air is very inefficient, simply because if you move 1 liter, as in volume wise, 1 liter of air, it does not have enough molecules in it to transfer enough energy. However, you move 1 liter of oil, it can transfer upwards of 1000 times more energy from point A to point B. So using that fact, using that advantage, we are trying to basically remove the middleman. And because we are still air cooling, we are still using refrigerator units, but all we are doing is instead of using cold air, we are using cold fluid. So that's all we are doing. So please be mindful of this. Don't say we are replacing this basically air cooling with completely liquid system. That is being tried out right now, because there are some solutions which using this oil or basically phase changing liquid, they're directly trying to dump the heat into sea. So those things are also being worked on as we speak. So suffice to say, all we are doing is removing the middleman and replacing the air system with a fluid system. Now many of you know there are two systems with this. There are first, which you have oil submersion. Many of you know type aquarium PC, you will get it. See, you have to understand about aquarium PCs is just that oil is there. It's not water. It may look like water, but it is not water. It's flat out oil. And we do not think anybody is going to use distilled water, no matter how non-conductive it is, because inherently it will become conductive over time and it's very dangerous. So suffice to say, mineral oil is becoming a very, very good solution for this. And many of you may have worries about it. What if it catches on fire? Because it's oil, it literally is flammable. Be mindful, or the power transformers have this. So suffice to say, if that kind of power load cannot make this catch on fire, your computer really cannot. So that's one method, using mineral oil. Second method, which is kind of a newer kid on the block, is that, as you can see, it is submerged in water, but hot parts, basically your processor, is boiling it off. So basically in this, nothing changes. Basically liquid remains the liquid, nothing changes. Here what's happening, that you submerge your computer into the liquid, the hot part as a processor in this image boils off, basically is changing the liquid from liquid to gas. Now this fluid is specifically designed, and I have provided link down below, that evaporates on much lower temperature, as in 30 degrees Celsius to 60 to 80 degrees Celsius. It does not need to reach as high as 100 degrees Celsius like water does. And depending on your processor, how hot it can run, because you have to make sure, if water like the fluid evaporates much too late, it may roast your processor, because your processor still has end up reaching the temperature where it starts to boil. So you want to make sure your fluid boils much quick, as closely as possible. So 30 degree to 60 degrees Celsius is the target, and you can find different mix in the market that will allow you to achieve that. So once this processor reaches 30 or 60 degrees Celsius, it starts to evaporate. So this fluid goes into gaseous phase and moves up in the chain. Now where it goes up, you have what's called basically a evaporator, basically a condenser unit for this gas, and evaporator is cooling that gas itself. Basically it's taking the heat away from that gas and dumping. By doing so, it's condensing the gas back into liquid and dropping it down. And if you are having hard time understanding it, think of it, this is heat pipe. All that it is, it's a heat pipe. It's literally like a heat pipe in your normal system. The benefit of this architecture, it does not require pumping mechanism, because this fluid keeps moving. You don't need pumping mechanism. You need some seriously strong pumps with this, because oil sometimes can make water look like, even though density wise it does have higher viscosity, which may sometimes correspond into much, you will need basically much powerful water pumps or fluid pumps for these sort of things. So this does not require pump, this does require pumps. So we come to why the heck we want to do that. If air is good enough that we have been using it so far, why the heck we want to compete against air? First, it's small and high density. To give you a context how what kind of power density we are talking about, this is a Cisco data server that you can buy, and this is a normal basically server unit, and it can store upwards of 400 kilowatts of processing power. Basically, if your computer consumes 400 kilowatt, this can handle it. Of course, it has external cooling and all that, but if you go for this, basically this is I have provided the link down below. This is a oil cooled system. This can handle upwards of 1 megawatt. This also has an external cooling solution. So as you can see, even though cooling solution in both scenarios are separate and both scenarios are taking care of the cooling somewhere else, they still there is still a huge gap, because if you try to cool this down to, like, let's say you dumped 1 megawatt of electrical energy here, you have to cool down the air to like minus 80 degrees Celsius, trying to extract the heat quick enough. In oil, that's not an issue. Oil can easily handle it. So suffice to say, you can see like both are container size, but see the power difference. Like in this you can put a low level supercomputer, in this you can barely put a data center. So second, it's very simple for architecture. Like as many of you know, because hot air rises, all the air conditioning unit have what's called two-phase, not two-phase, I would say, two-path cooling solution. Basically, they collect the hot air from top and distribute the cold air from bottom. This was not done in old data center, but nowadays it is almost compulsory in all data centers, because the cold air is being released from the background. That means your floor is elevated floor. It does have some extra advantage that it allows you to route cable under the floor, and because which is much easier to access compared to on top of the floor. So suffice to say, there are some advantage, but as you can understand, this means you also have to build a completely independent floor. So it's very expensive and low noise. Because this thing is directly dumping the heat away from the system, there is no need for fans. Basically, you might say, okay, it needs pump. Pumps are like, one pump can easily handle 100 liters per minute very easily. these use a big pump, and in terms of noise level, they can barely they're gonna barely produce 60 decibel, and some pumps that itself is submerged will produce almost 30 decibel. So suffice to say, it's whisper quiet versus this is gonna be loud. To give you a context, like servers generally end up reaching 70 to 80 decibels of power. To understand that this is not lethal, this is not painful, but if you are exposed to this continuously for long enough time, as in like few days, you're gonna damage your hearing. And many of you have seen Google data centers, people always have to wear hearing protection because it will damage you over time. Not just like, you went in there, okay, now you are deaf. It takes time, but this also saves that. And this means whenever somebody is working there, they don't need hearing protection, meaning people can communicate much more easily, much more comfortably, and that noise simply means you are wasting energy. Here it's not happening. So you get that. At the end of the day, nobody cares about anything but money. So money comes from the fact that it's saving power. Because it's cutting out the middleman, the energy efficiency is upwards of 3 to 5 times more. So that's a very significant cooling cost. Imagine like you're spending $100 per hour. Now you have to spend, let's say, $10 to $30 per hour. That's a significant saving of energy, which will translate into significant saving of your capital, your money, your profit, basically the thing that actually matters. So power saving is the final aspect. That's why anybody is even bothering to do it. That's why even Intel started to mass produce components that can be used in submerged PC. There are other companies like HP and Dell, they are also jumping into the fray, and you don't actually need to change anything. It's just they want to optimize the system. So I want to illuminate the fact that there are two solutions for this. One, you have oil, another you have phase change. Now in phase change, as you can see, you don't need a pump because it acts like a heat pipe. The thermal energy itself is doing the transfer movement. Basically the moving of the fluid is directly happening because of the heat itself. So you don't need pumps in this. But if you have something that is consuming a lot of power, this is not a good solution. So imagine this can give you, let's say, per rack, it can give you upwards of, let's say, 100 kilowatt. If you dump something that is generating heat upwards of 200 kilowatt, this will not able to handle it, simply because it will evaporate way too quickly. And not to mention, let's say for some reason your cooling tower or this cooling system fails, it will boil it off way too quickly. Oil can handle that high temperature for a very long time. As many of you know, transformers internal temperature can reach as high as 50 to 100 to 500 degrees Celsius. It can still handle it. So this will not, let's say your cooling system fails, basically this system stops working, you're basically not only you're gonna have a risk of explosion, not explosion as in like fiery explosion, but pressure explosion, because there is vapor being built up. As your fluid will go down, your components will be completely exposed with no cooling. So this is very crucial to understand. This is why not everybody is jumping into this. It's because this cannot handle very, very high heat load. Now if you have moderate heat load, this can easily take care of it, and you will save extra money by not needing pumps and not needing to circulate the fluid. So but be mindful, because this goes from liquid to gas, you lose this much more quickly. Your oil will also evaporate. You will also suffer loss in oil system, but that would be like, let's say in 1000 liter system, you will lose 1 liter per month. Here you will lose 1 liter per day. So this is very mindful. Unless it's completely sealed, you're gonna lose coolant much more quickly than oil system. So this is the balancing act. If I have to put my money on, I'll put my money on oil system, simply because A, it can handle much higher heat loads, B, the loss of mineralize is much more easy to control, and not to mention it's also cheaper. So what we can expect in the future? One thing you have to understand, the current generation of computer, as supercomputers we have, they don't need it right now, but as 2 to 3 generations from now, it will be compulsory. You have to do submersion cooling, otherwise flat out you will not able to build supercomputer compact enough. You can still build it, you just have to spend it out, spread it out over a large area, and your power consumption will be equivalent of a small city. As many of you know, these things already consume megawatts of power just for cooling, not for anything, just for cooling. So it will become a necessity for it. Second, SSD. Right now, all you can do is dump the processing node. You can't dump the data node. Basically, you can't dump hard drives, because hard drives have what's called airport, and it's there. So because to balance out the air pressure in the platter while the platter is spinning very high at high speeds and temperature balancing. So it has a port that if you submerged your hard drive, it's gonna die. So for that reason, if SSD starts to become the mainstream, the next thing basically, SSDs will be very easy to done. Now many of you may ask, SSDs are not very power intensive, so they may not need cooling. Yes, if you're talking about one or two, but if you're talking about, let's say, each SSD, like this SSD, it's 100 terabyte SSD. Now it's not 2.5 inch. That 2.5 inch largest capacity is reserved for Samsung 18 terabyte. This is 3.5 inch, and this is very slow. This is not meant for high speed. This is meant for like data archiving. So this has only SATA 3 level speed and 3.5 inch form factor. So this consumes, let's say, 5 watt of power. Now imagine 1000 of these, that you're talking about 5 kilowatt of energy. And because if you don't dissipate it quickly enough, it will start to affect whatever components that is around it. So for that reason, these also need cooling. Now once SSDs become like, at this point they are already reaching a point where it's like just a matter of time that all the hard drives in the world, in servers, in your computer, will be replaced with SSDs one way or the another. Question is how many years, 5 years or 10 years, but this will happen. So the moment this also storage unit also goes hard, solid state, you can dunk those also. Second, right now submersion cooling, while it does save money, it does not save your capital investment. Even though you are saving capital investment when you are building the home, the component itself hasn't reached large enough mass production that it would be cheap enough. So we still have to wait for it to become cost competitive. Right now it's almost reaching there. Like running cost is already down, however the raw capital investment is not low enough yet. So we have some room for growth. So this was my presentation on submersion cooling. I hope you liked it or learned from it. In that case, please leave a like. If you didn't, don't worry about it and dislike it. And I would urge you to comment and share it amongst your friends who may be interested. And as always, thanks for watching.